So, hello SecT, good morning. I'm really glad to be here with you today. And I'm really surprised that it's still 9 a.m., the second day after party, and you aren't that many, so I'm really glad and honored. And my today's talk is Broken Isolation, Draining Your Credentials from Popular macOS Password Managers. So, my name is Wojciech Regula. I'm a head of mobile security. There is my presentation, but this doesn't work. But anyway, I have 50 plus CVs in Apple, so I spent way too much more time on it. I'm focused on iOS and macOS application security. I'm an author of Certified iOS Application Security Engineer course. I document all my findings on my blog, which is wojciechregula.blog. If you don't want to use my hard Polish unspeakable name, just use the alias osx.zip. I own this domain, so there will be a redirect to my blog, no worries. And somebody of you may also know me from an iOS security suite, which is an open source Swift library that helps developers making sure that their applications are run on secure iPhones. And I really enjoy speaking on conferences, so you can meet me on Black Hat, NullCon, Objective by the Sea, DEF CON, and other conferences. So today's agenda is that I'm going to start from the introduction you to basic macOS security assumptions, let's say, assumptions. And then we're going to talk about macOS security and isolation mechanism, and this is really crucial to understand. I will elaborate on it later. And then we're going to go through pawning some popular macOS password managers. And the list of the password managers is made deliberately like that, because you will see that each password manager has been written in different technology. There is a different context on how each of those password managers work. And you will see that the thing I'm going to show you is a 0-day, end-day, maybe a feature. I will leave it to you. And you will get it after you see this talk. And because I don't like leaving, especially developers, with a problem, I will give you some recommendations. If you code any macOS apps, there will be some portion of information to you how to fix that features, vulnerabilities, you will see. And at the end, of course, conclusion. So just to introduce you, before, when I was younger, I gave 3 talks on Black Hat. The first talk was 20 ways to bypass your macOS privacy mechanisms. Then, a year later, I gave a talk, 20 new ways to bypass your macOS privacy mechanisms. And 2 years later, I didn't have an idea for a title, so I just titled it Unlimited Ways to Bypass Your macOS Privacy Mechanisms. But these talks were like 3 minutes introduction, and then 20 bugs one by one with exploits. It was fun, but still I was observing the very same bugs in applications that I've been tested and macOS, and I'd like to do a talk with let's call it a mission, an educational talk about how these boundaries, how those security assumptions on macOS work in general, because macOS is not a Linux, but it's sometimes treated as it was a Linux, but it's not. The boundaries are totally different. So let me quickly introduce you to the history. And there will be prepared. I know it's still 9 a.m., but be prepared. There will be like 30 slides about theory, about the boundaries, but then I promise we're going to get through exploitation. I will show you some exploits. But in order to understand the exploits, you must understand the boundaries. So, history. As I said, chart of the history taken from Wikipedia. So, we have Linux in here and macOS X in here. There is a different branch, you see. So, there is a FreeBSD, which is ancestor of macOS, and NextStep was also an ancestor of macOS. That's because of Steve Jobs changed companies, etc. So in the end, we have macOS, which has a hybrid system. it has a monolithic FreeBSD kernel with a Mach microkernel. So we have a hybrid kernel with two different boundaries, two different security assumptions, two different security ideas. So for example, in Mach, the portion of the kernel which is responsible for processor scheduling, multitasking, virtual memory, interprocess communication, Mach traps, which is like syscalls on Mach. And then you have the BSD part, which is responsible for process management, signal handling, user and group management, syscalls, TCP IP stacks, and sockets. So Mach and BSD each maintain different security models. Mach's security model is based on ports, whereas BSD's security model operates based on process ownership. So you can see now it's not like the same. We have two different assumptions in very one kernel, right? So that lead to vulnerabilities because it is not that consistent, especially to people that code the applications. And macOS X, the original one, had many children. So we have macOS, iOS, watchOS, tvOS, visionOS, iPadOS. But the kernel at the very bottom level is almost the same. It mostly differs in kernel extensions, but there's the same blood pumped by the same heart. So please think about it as it was like the same kernel, the same assumptions. And many years ago, Apple created such a graphic. And we're going to go through it so you will better understand how all these Apple operating systems work. So the first question to wake you up, who uses any of Apple security products, just products? Oh, so I would say like 50% of the audience. That's good. That's good. So let's start from the hardware and firmware. We have a kernel. Now we know it's a hybrid kernel with Mach and BSD layer. And in the kernel, it communicates with two different chips, at least with two different chips. The first one is Security Enclave, which is a hardware-based key manager that's absolutely isolated from the main processor and provide an extra layer of security, of course, because crucial security operations are delegated to the main, to the separate coprocessor, right? So it's even if you get a kernel exploit, there's another chip you must exploit to perform some security operations. And then you have a secure element, which is also a separate chip responsible for electronic payments, like, for example, Apple Pay. And this communicates, the kernel via crypto engine communicates with those chips to get, for example, device key, group key, Apple root certificate, etc., etc. And on the software level, we have a file system. We have OS partition. And OS partition is something that's not encrypted. It's sealed. There is a signature of the operating system. And nowadays on macOS or iOS, you don't even have access to this mounted OS partition because what you see is a snapshot of it. It's read-only, so you are not able to modify at all the OS partition without a proper exploit. And then you have user partition, which is encrypted, and only this user partition is encrypted. And in theory, on macOS, you have applications that are not sandboxed and applications that are sandboxed. But the truth is, we all live in a hallucination. Because there is something called system integrity protection, which is a global sandbox over all of the applications that run on macOS, iOS, etc. But on macOS, even if you deliberately, in Xcode, you specify, I don't want my application to be sandboxed, that's a lie. You are still in the sandbox. We all live in a hallucination. So whenever you put an application in the sandbox, it has some consequences, like isolation. So before macOS Sonoma, when you put an application in the sandbox, it meant that your application cannot break out of the sandbox and access resources outside of the sandbox, right? That's how you are probably think that sandbox work. But from macOS Sonoma, it has been changed. Like sandboxing an application means only that any other application, even though they are unsandboxed, should not be able to access your application. So a sandbox now work for both ways. So you cannot do some operations from the sandbox and outside of the sandbox on the application. So yeah, this is how the security model works. And the user partition, which is a separate partition, that's a good idea because, for example, if you wipe your iPhone, the OS partition gets untouched, right? So this is why it's that fast. So the basic things to understand at the beginning. macOS is absolutely not a Linux. And applications that run with the same UID should not be able to control themselves. This is really important. On macOS and on on Windows and on Linux, there's absolutely different assumption. And I will briefly, in some slide later, I will show you what are the consequences if this isolation assumption is broken. So if you code an application and you want your own application to be controlled by other apps, like for example debuggers, it must be signed with a special entitlement. So me as an application, I need to say, I want to be debugged. If I do not specify the entitlement, some other things will happen. I will show it to you later. And you may say, all right, but macOS is POSIX compliant, so there is a ptrace syscall, right? And with ptrace, we can control other processes when we are root. But that's not true. On macOS, ptrace is implemented, but it's not implemented as it is implemented on Linux. So even though there is a ptrace syscall, with the ptrace, you should not be able to control other processes. If you are able to change the code execution flow with ptrace, let me know. That's probably a vulnerability. So let's now talk about macOS security and isolation mechanisms. So why the cross-process isolation is that important? Because without such an isolation, if you, for example, are able to impersonate private entitlements, which you may have an application running with a user UID, but the application has some special private entitlements. What does it mean? It means, for example, that we are able to bypass TCC, which are the whole privacy restrictions. So, for example, if you install an application on your iPhone, like Microsoft Teams or Zoom, and you want to open the camera to start recording, there will be a prompt, right? The application wants to get access to your camera. And you may click OK or don't allow, right? So on macOS, there's the very same mechanism. That's also called TCC, transparency, consent, and control. And the assumption on macOS is that even if you are a root, you should not be able to click on this prompt. Apple even detects on those prompts synthetic clicks. So if you are able to move your mouse programmatically, you should not be able to click this prompt. Is that important? Is that crucial? So without isolation, if you have, for example, a Microsoft Teams, and you are able to somehow control that process from another application, you may, if it would be possible, you would be able to get its permissions, right? The permissions that user click in Teams. OK, I allow accessing camera. So that's problematic. And what else may happen if you impersonate private entitlements? Well, you may elevate your privileges from user to root. So that's by default. That's the system behavior. Because if an application has some private system entitlements, it may perform an inter-process communication to a process which, for example, executes a command as root. And this is absolutely fine because Apple has full control over the private entitlements. So this may happen also. And if you have the private entitlements, you may also grant you an entitlement that allow the SIP bypass. So the whole hallucination I told you some slides ago, that we all live in the sandbox, will break because you may bypass SIP. Or even no bypass. You may have an entitlement that just ignores the hallucination sandbox. What else could happen if you have the ability to break the isolation? You can trick third-party XPC services to perform user-to-root LP, or inject to third-party apps to get the TCC permissions, like I said. So it's kind of complicated, right? But the good thing is that Apple made a white paper called Apple Platform Security White Paper. You can download it under the following link. But unfortunately, not everything is very good documented. It's on general level, the Apple Platform Security White Paper is really great. But if you want to dig to the details, because you want to, do some vulnerability research or something like that, you need to perform some reverse engineering. So let's now talk about the system integrity protection, the great hallucination sandbox. It must be enforced on a very low level because we want even system applications to be in the global sandbox. So it's enforced on the kernel level, and it's based on sandbox kernel extension. And it will restrict access, the sandbox, to many directories on macOS. This is the thing that's responsible for denying debugger when you want to debug some Apple-signed processes. And system integrity protection is also known as rootless, because even if you are root, you should not be able to do the above-mentioned operations. That is that important. And last thing, are there any macOS developers in here? OK, not so many. So I just tell you, for regular macOS users, if you sometimes face a problem and you Google it and you find maybe an answer in Stack Overflow, and the most voted answer will be, well, just disable SIP and everything will be fine and your problem will be gone. Please do not do it. Without SIP, everything on macOS is possible. Like, there is no global hallucination sandbox. And your application or a malware will be able to do all the things I told you before. So they will be able to elevate from user to root. The whole TCC, the whole privacy framework is turned off when SIP is turned off. So please do not do it. And I've seen such a high-voted answer on Stack Overflow too many times. Because yes, it solves the problem, right? If something on a security level doesn't work on macOS, if you kill the global security mechanism, everything will work, right? So yeah, that works, but please do not do it. How can you see if system integrity protection is turned on? Just with CSR rootless status. So if you manage an organization with macOS stations, please do it globally and check if there is nobody who changed SIP to be turned off. OK, so let's do an experiment with the isolation. Let's inject, for example, to LogDaemon with Apple's own debugger, not our own, just regular Apple's own debugger that's called LLDB. As you can see at the screenshot, we are root. And we just call LLDB with the PID of logd. And let's take a look what happened in the console. The debug server wanted to get task for PID for the PID of LogDaemon. There are some logs, and in the end, we can see that attachment has been failed. And what is the task for PID? PID is a thing from the FreeBSD kernel layer, but what is a task? Task is like a process, but in the part of the Mac microkernel. So you can see, even if we want to control a process, there will be change of the words, right? We're changing from what we know from POSIX, PIDs, to tasks. And while we have a task part, we can fully control the process. We can mess with its memory, et cetera, et cetera. So yeah, by the end, it failed. So why did it fail? Because debugging a process, which gives us the clear way to control the process, requires task part of the debuggy. And as I've just said, it involves using the task for PID function. And task for PID is allowed only under some critical circumstances. And you have to know also that the task for PID requests are controlled by taskgate daemon and MFI, which stands for Apple Mobile File Integrity Daemon. So when SIP is enabled by default, and you can take a picture of it because that's, if you want to do some macOS security research, this slide will help you a lot. I wish I knew it before I started my research like 7 years ago on macOS. So the task port retrieval is not possible when the target app is a platform binary or has a hardened runtime. And regarding hardened runtime, I elaborate on it later. But generally, if you want to debug an Apple-signed process, that should not be possible. If the debuggee, so the process we want to debug, holds a public getTaskAllow entitlement, the injection is possible even by the same user, so no root is required. And this is the situation when we have an Xcode and we said, yes, I'm still in the process of development my application and I want this particular entitlement to be put into the application because I want to debug my own application, right? But that's also complicated. It sometimes exists on production, so if you ever will be pen testing any macOS apps, make sure that this entitlement is not present. If the debuggee doesn't have hardened runtime and was signed without the getTaskAllow entitlement, the injection is possible, but you need a root. And the injection is always possible when debugger app holds a private system task port entitlement. And this is just for your information. Even Apple-owned debugger, the public version, does not have such an entitlement. So, yeah, unfortunately. If you ever find such a process that, or such a debugger that may have the system task port, the private entitlement, it means that probably there is a malware or there is a backdoor placed by Apple, because no debugger, no public debugger have such an entitlement. But can we just impersonate some private entitlements? Let's see. We have a Hello World application. Those are the entitlements. That's a private TCC manager entitlement. As you can see, become Apple private, which means it's private. And with code sign, we see that the Hello World is not signed at all. And in that line, we just sign it with the entitlements. But if you want to spawn the application, the Hello World application will see that it will be immediately killed by the operating system. And you will see that's because M5 told us restricted entitlements not validated, bailing out. So unfortunately, that happens when you have SIP enabled and you want to impersonate any of those private entitlements. When SIP is disabled, that will work. That will work. And there's a fun fact. Back in 2020, in Big Sur beta, I spotted some Apple binaries with getTaskAllow set to true. So I was able to get the task port of those Apple's own executables and impersonate their private TCC permission. So Apple paid for a bounty for that, and I found like 5 or 6 binaries having that. And you can see the proof, because with sudo in LLDB, I was able to get access to the process. So yes, because Apple knows that the user root boundary is not that important on macOS, because when you have SIP, root is not really a root as you know it from Linux. Apple pays for such bounties. Apple pays for such vulnerabilities, because yes, there's another boundary with it. Great. So if we want to inject our code to third-party apps, because we'll be slowly getting to the password managers, we will be looking for apps with getTaskAllow, those applications that deliberately say, I want to be debugged, or applications without hardened runtime. But what is the hardened runtime? The hardened runtime, along with the system integrity protection, protects the runtime integrity of your software by preventing certain classes of exploits like code injection, dynamically linked libraries, hijacking, and process memory space tampering. That's a copy-paste definition from Apple. But just for your information, too long didn't read, blocks code injection. Hardened runtime is for blocking code injections. Yeah. And nowadays, all software from the internet must be notarized. And notarization is a really broad mechanism, because Apple requires you, if you want to put your application in the internet, that you must send your application to Apple servers. They will check it against malware. They will check it against if it has the get task allow entitlement, because as we just said, we don't want any other application or production to control our application. And they will also see if there is the hardened runtime turned on. So theoretically, all the password managers, because they are not delivered with the system, are downloaded from the internet, should be notarized, right? And there is even a prompt in Apple documentation that to upload a macOS app to be notarized, you must enable the hardened runtime capability. So in theory, everything should be fine. Every password manager should be correctly isolated from the rest of your applications. And how the hardened runtime is enforced? It's enforced by setting a code signing attribute, which is CS runtime. So you apply the hardened runtime during the code signature process. And as the XNU, the kernel is open sourced, you can even read it, exactly how it was coded. If you're interested in macOS security research, I will really encourage you to read the sources. Unfortunately, not everything is in there because macOS relies heavily on sandbox extensions. And because of the license, sandbox extensions do not have to be open source, so Apple, of course, didn't open source them. Great, so how can we see that hardened runtime is turned on? We can just use the code sign tool to do this. So we just use code sign -d-v with, for example, GarageBand, and you will see that, okay, there is a flag called runtime, so that's hardened runtime. But is the hardened runtime the holy grail of giving us the isolation? No. There are runtime exceptions. So even though you have a hardened runtime applied on an application, there is plenty of different exceptions you may put on the application. So, like for example, JIT compiled code entitlement, you may allow unsigned executable memory entitlement. But from our perspective, if you want to just inject our code to the first-party applications, we are interested in those two. So allow DILT environment variables entitlement. So who of you knows the LD preload environment variable from Linux? OK, so not everybody, so I will quickly explain it. LD preload is an environment variable, and you specify a dynamic library that will be loaded when the application is launched. So with this one, you should be able to make an application load a dylib, dynamic library. But normally, if the hardened runtime is turned on, macOS will deny loading a library that has been signed with a different developer certificate. So we also will be needing this one, disable library validation entitlement. If it's set, macOS will happily load the dynamic library to the process which is hardened. So how can we see it? Also with code sign. So we -d -- entitlements, and for example on Firefox you will see disable library validation turned on Firefox. I reported it to Firefox in 2020 or something. Well, generally macOS browsers are not well known for proper isolation, so Firefox developers told me they must enable this thing because there are Flash plugins. And I said, it's 25 or like, in what year we live? But yeah, that was the explanation of them why the entitlement is set to true. So just to sum up this part, and I promise you we're gonna get now to the exploitation. I know there is a lot of theory, but I told you that's a talk with a mission, an educational mission, because I wish I saw such a talk 6 years ago that is really important to understand, and you cannot like freely read it in Apple's documentation. So those all circumstances that must happen to control other applications are really important to understand on this part. But however, just to sum it up, we'll be interested in password managers that have get task allow or are without hardened runtime, or are with hardened runtime but have the useful runtime exceptions, and have some custom debugging features that don't depend on get task allow. And here, wink, wink to Electron. So if you thought that Electron as a framework is bad, you have one more argument to that list of problems with Electron. And just for your information, all those techniques that we'll be using against password managers can be used for exploiting any other applications. Like you may play bug bounty programs using this knowledge. Like there is plenty of applications, of really well-known applications like antiviruses that also have problems with those things I've just told you about. So the research is absolutely not complete. It's not like it's fully have been exploited and there is no thing like that. It's everywhere. So I just put password managers in here to attract the presentation, to make it more sexy, because we all know we all want to hear about attacking security products. But as I said, that's a talk with a mission, so that can be used against any other software on macOS you have. So let's spawn finally the popular password managers. And we're going to start from a MacPass, which is a native macOS KeePass client written in Objective-C, so purely native application. It's available under the following GitHub website. And it has like 6.7K stars, 450 forks on GitHub, pretty known password manager. I personally use it. And when we use code sign on it, we'll see that, OK, it has hardened runtime turned on. That's good. But we have disabled library validation and password manager. And maybe that's it, right? Maybe we can just change one of its dynamic libraries, and maybe that's win. Or maybe we have successfully exploited it. But no, there is another mechanism I didn't tell you about, but that's the last mechanism I'm going to talk during this presentation. I promised it to you. So with macOS Sonoma, there is something called app protection. So I told you at the beginning about the sandbox. So if you put your application in the sandbox, the additional sandbox, your files of your application will be protected as well after first launch. So only a process that is signed with the same developer ID will be able to modify your own application. And this is because, for example, you want to code an updater, right? An updater must change files of the application, and it's signed with the same developer ID, so Apple said, OK, that's fine. But why, in general, MacPass disabled library validation? Because it allows loading custom plugins. For example, you want to unlock your password manager with your Face ID or Touch ID. So there must be a plugin functionality that allows, implementing new functionalities in the MacPass. And plugins are stored in library application support MacPass, so they are not protected. And this is on purpose. Think of it as on Windows, for example, you have app data. It's not the application container. It's just a directory that the application may use to get some information or to exchange it with other applications, etc., etc. So this is on purpose not protected. This is a feature, not a bug, feature. So we can abuse that feature to create a malicious plugin that can drain all the entries once user unlocks the vault. Let me show it to you. So we are in the temporary directory. We now verify if the hardened runtime is turned on. It is. Let's take the MacPass's bundle identifier. And using defaults, we can read its defaults. There is the last database path, so we know exactly where the entries are stored. And now enable the plugin loading functionality, which is load incompatible plugins to true or 1. Great. Now let's copy the plugin to the directory I just told you about. And now just open MacPass. MacPass has been opened. And now user unlocks the vault, and then you will see two files created in the temporary directory. So you will see all the credentials stored in here. And also the master password will, of course, contain master password. Great. The exploit was pretty easy. I just created a dynamic library that, after it's loaded, it immediately calls this constructor, which exchanges an implementation of a function that unlocks the password manager, which in the end just unlocks just gets the password and calls the original function, so user will not even spot that something wrong happened in the meanwhile. All right, so a question to the audience. Who thinks that this was a bug or vulnerability? Okay, I would say like 30% of the audience. So you can see it's not really easy to determine if it is a bug or it is a feature. Certainly, there should be an isolation I told you about during the first part of the presentation. But you will see that things are not that easy on macOS. So let's take a look at Bitwarden, which is an open source password manager with a premium plan. It's written in Electron and is distributed via Mac App Store. So the first thing we do on macOS when we audit an application, let's see the code signature of it. Flags none, no hardened runtime in newest version of Bitwarden. But didn't I just tell you that all applications downloaded from the internet must have the hardened runtime? I told you about the notarization, the enforcement, Apple anti-malware stuff, etc. And here we have a password manager with hardened runtime turned off. How did it happen? Yes, because I told you that applications that are directly downloaded from the internet. But Bitwarden is distributed via Mac App Store, which is not like you download an application by your browser, by, I don't know, an attachment from Microsoft Teams or something like that. And Mac App Store does not enforce the notarization because Apple say, yes, but we have a different anti-malware mechanism in Mac App Store, so we don't need to audit the applications in Mac App Store just like we do if a developer wants to distribute it on their website. Interesting, right? And we can simply inject a dynamic library to Bitwarden because the runtime is absolutely not protected. There is no isolation between the operating system and Bitwarden. So does it mean that software downloaded directly from your browser is more secure than this downloaded from the Mac App Store? Such an irony, right? So maybe that's a mistake by Apple. Maybe that's a vulnerability in Mac App Store. Maybe I should have reported it to Apple. But let's take a look at the documentation. We are in embedding a helper tool in a sandbox app documentation. Add the hardened runtime capability, which is not necessary for App Store apps, but is best practice for new code. Not necessary for apps distributed via App Store. So how can we exploit Bitwarden? Simply, just start the logs and just, let me come back in here. We just use the open function with env to, insert the dynamic library. Then we have Bitwarden. User provides their password. And I just put a simple keylogger that logs it, nothing more. So we have the password to unlock the vault, and we can steal files from Bitwarden and just unlock it on our own, on our computers. The keylogger is pretty straightforward. Like everything I do is mostly on my GitHub or gists on GitHub. So you can find me on GitHub and just download it. It's a really simple keylogger. So the next question to the audience. Was this a feature or a bug? So who is for a feature? OK. And who thinks this is a bug? Well, now most of you think that it's a bug, but is it? There is a clear, information in Apple's documentation that it's not necessary to do it in macOS App Store. So let's take a look at NordPass, which is also written in Electron, but is directly downloaded from the internet. So by directly downloaded from the internet, I mean you used your browser to do it, not Mac App Store. And here, critical Electron fuses are turned on, what allows code injection. If you want to know more about the Electron fuses, last year I had a talk on DEF CON where I automated the whole process and released an open source tool that just auto-exploits Electron applications and gets all the TCC permissions, but it's all open source. So if you'd like to dig more in it, just watch the talk. But generally, use such a command to see if there is Electron fuse, a critical Electron fuse enabled in an Electron app. And as you can see, there is enable node CLI inspect arguments, which is enabled for NordPass. But hello, Electron applications are like applications with embedded browser, right? And browsers provide functionality that you can, for example, open dev console, right? You can place your JavaScript script in it, execute it, right? This is how browsers should work, right? So if Electron is an application with an embedded browser, is it a bug or a feature? You will determine in a moment. So let's exploit it. I will be using my tool that I just told you about. So before I do so, I just export to nvar, so the exploitation will be easier. And now my electronizer, my tool, that will open the NordPass master password stealer. There is the WebSocket server started by the Electron application. There are dev tools, but just via WebSockets. User authenticates. We have all the items. And now let's see if the master password has been dumped. Yes, we have the master password. So again, we may perform the same technique we did before with Bitwarden. Just use this key to decrypt the vault. And the exploit is purely a JavaScript file, because we just opened DevTools and executed JavaScript code. So again, a question to the audience. Who thinks this is a vulnerability? No. Always 50-50. You can see that's not that easy. I encourage you to discuss it after the talk, if this is a bug or this is a feature. All right, and the last password manager, the one before the last one. The KeePassXC, which is downloaded from the internet, completely open source. It's native because it is written in Qt. And it's very well documented. If there are any developers of KeePassXC on the audience, big kudos from me. That's a really great password manager. But because I wanted to show you different perspectives on that problem, now we're going to talk about a browser plugin. So there is a plugin that you may install in your browser. And under the hood, there is some asymmetric crypto. It is all documented, but I will not bore it with you. Just you may just understand that we know the connection name and the private key, nothing more, to impersonate such a connection. And I told you that macOS browsers are not really well known for proper implementing isolation. So we can simply get the local storage logs, the private key from it, and spoof the connection. Just open browser files. Browsers on macOS except Safari are not sandboxed. So you can access their containers, enter some local storage, and just get the private key and the connection name. That's that easy. So let me show you the demo. We have the KeePassXC. This is the whole code. Somebody created even a Python package for it to communicate with the main KeePassXC application. Thank you, the developer. And this is the command I just used to get the connection name and private key from the browser files. It's not sandbox, but the browser is not sandbox, so it's a feature. And yeah, we were able to get the entries from the password manager. This is the whole exploit, really easy. Who thinks that it's a feature? This thing. Who thinks this is a bug? OK, 50-50 again. There is nothing wrong with KeePassXC, right? They implemented everything correctly. There is a asymmetric crypto communication. Everything is verified. There is no vulnerability like we can impersonate something. We have the private key, so that's the browser problem, how it stores it, right? Not that easy. And the last password manager is Proton Pass, which is a plugin-only password manager. There is no standalone macOS app. It lives only in the browser. So all encryption, decryption happens in the browser JavaScript runtime. And here we can just use Selenium framework to automate browser and get all the entries that are decrypted in the runtime. Nothing complicated. Again, NordPass. It was their decision to make it as a plugin, right? The exploitation is finished. It was that fast. It was their decision to do it like that. But again, this is probably not a problem with the NordPass itself. That's maybe you can say that's a wrong architecture decision to make it as not a standalone application, but a browser plugin. But again, there is a problem with browser isolation, not with the Proton Pass itself. So yeah, I encourage you to open a discussion after my talk. But here we need to sum everything up because we are out of time. So at the very beginning, I told you about the basic macOS security assumptions. macOS is not a Linux. Security by isolating applications processes are really important on macOS. You now know it. So if there is no isolation, you can impersonate privacy entitlements. You can elevate your user to root. There are many possibilities if the isolation is not turned on. So we went through some different password managers written in all different technologies or downloaded from the different context. I still don't know which are features, which are vulnerabilities. I leave it to you to discuss. But I told you at the beginning that I don't want to leave you without recommendations. So some crucial points. Enable hardened runtime, review hardened runtime exceptions, enable sandboxing because now it will protect applications from the outside to not get to your app container, notarize your applications, not only installers, if use Electron, disable problematic fuses, and pen test your apps. And as I told you, I'm a creator of an iOS application security engineer course for pen testers and developers. So I created a 10% discount for SecT community. So if anybody's interested, feel free to use this discount. And that's it for today. Thank you very much for your attention.
Thank you very much, Wojciech. Yeah, that was a lot of interesting information in there. I was actually very impressed. Because I read the submission as it's like all the password manager things, but then you got the whole lecture about the actual security.
Yeah. The password managers was only a trick to listen, just to trick you to listen to this presentation because I needed to give you something, sexy password managers, but I wanted to give such an informational talk about all the boundaries. The public must finally understand the problems because my first presentation was about pwning antiviruses, and we spotted isolation problems in like 80% of all antiviruses on macOS, and we were able to elevate our privileges from user to root just by breaking the isolation. So please spread the knowledge. Playback bounty programs, earn money on it. The research is not over.
Well, we were absolutely very, very happy to see all that content in there. Thank you very much. Again, this is time for break, so say thank you again to Wojciech.